probably through this.
Hey, good morning. So welcome back to MAE Seminar. So today we invited Professor Li from University of Texas, Austin. So his research encompasses a broad spectrum of very practical areas of the nanocomposite and the nanomaterial and the manufacturing. And he's also has served as a committee member and board member of the North American Manufacturing Research Institute, NAMLAC. And also he was an awardee of the Presidential Early Career Award for Scientists and Engineers in 2005. Today, Dr. Li will introduce his research about the road-drawn transferring of the graphene. Thank you.
Thank you, Jim. It's a pleasure to be here to give a talk to share our research. As introduced, I'm Wei Li from UT Austin. I would say right now it's similar weather. Temperature is very nice. If you want to go to Austin, go in the season, spring season, not in the summer, because summer is going to be very hot. But it's a very vibrant city now. As you can probably heard from the news, Austin is growing a lot in the past 10 years. And a lot of new industries going into the city. So I've been there for more than 10 years, seeing the growth of Austin. Before joining Austin, I was at Washington, so I spent 9 years in Washington, Seattle, which is a very different climate in Austin, but I enjoy both places. So today, it's my pleasure to share, by the way, thank you very much, John, for the invitation. And so I'm going to share my research over the years, starting from Washington, Seattle. Okay. So the first slide is my research overview. So basically, my lab is doing nano and biomaterials processing and manufacturing. So my background is manufacturing person. I do nano and biomaterials. So on the left-hand side of the slides, you can see it's all related bio applications. So the first, the major application was we do biomaterials, so we can create porous polymer materials, and then we can create interconnected porous materials, and then do not use any organic solvent. So it's a solvent-free fabrication method. We can create controlled pore size, controlled porosity very well. And then because it doesn't use any organic solvent, so you can use the material for cell seeding. You can allow cells to reformulate in the scaffolds. We can also make the polymer foams in selective areas. So we do selective ultrasonic foaming. So on a polymer chip, we can selectively make 3D scaffolds, and then we can carve channels between the scaffolds, and then we can circulate fluids through it. So make it an in vitro tissue model system. We use it for drug study. So we were able to demonstrate using the cell culture, liver cells, and the cancer cells, and we connect those two chambers together, flow through drug, so we can study the drug toxicity effect, going through liver, without liver, what is the effect. So it's very useful for drug design. You can study the effects of pro-drug and regular cancer drug. So that's part of the research in 3D microscale tissue model system. And currently, I'm still working on a smart bio-related project. It's a smart surgical tool device. So these devices are called the electrosurgical tools. So you have tweezers. You pass through high-frequency electricity. You use it to seal blood vessels. So it's very useful for robotic operations, for laparoscopic surgery. So you use Da Vinci robots, and then you stick bipolar tool in it. You can seal blood vessels. You can also seal large diameter vessels. But that's still a research field, how to seal larger diameter vessels. And our work was sort of like a smart manufacturing. We introduced sensors on the surgical tool. So we can tell whether you're making a good steel, you're overheated, or you're underheated. So to avoid patient, later on problems in the post-recovery process. And then there's another project. It's a wearable electronics. So we make, this is a knitted sensor device. We integrate a knitted sensor into human garment, and you can wear this garment. This sensor will sense strain. One immediate application is for dysphagia application, so people who have problem swallowing food, So we use that sensor to detect whether there's a swallowing action or there's any problem with swallowing action. On the right-hand side, this is mainly related to nanomaterials. So we have been working on multifunctional polymer, nanocomposites, and nanofoams. So we can blend nanoparticles into polymers, and then we can make foams in these polymers. So we are making multifunctional materials. These materials are light, electrically conductive, or you can discharge electrostatics. So need for this was in Boeing when they developed Boeing 787. They want to have the interior to be multifunctional, to reduce weight and avoid electrical charge. So also this work can be used as, we make this membrane. So because of nanoporous, we can use it, we can make a membrane. So this membrane material can be used in fuel cell applications, in battery applications for separators. So that's another application area. It also can be used for water desalination. And currently, this another project we have been working on for a long time is graphene transfer and application. So we build a large-scale roll-to-roll transfer machine, and we study the transfer process. We take graphene off of the gross substrate, which is copper. So we grow monolayer graphene, and then we separate, we delaminate graphene and transfer it onto polymer substrate and use it for further applications. We're also looking for applications using graphene. One of the major area is graphene-based field effect transistor. So today's talk is going to be focusing on the graphene transfer and applications. I'm mainly going to introduce our work, graphene-related, large-scale graphene-related work. So as you probably know, that graphene is a single-layer carbon atoms. It has been touted as a wonder material. It has a lot of applications. If you look at the property comparison between graphene and competitors, so mechanical property, Young's modulus 1.1, 1,100 gigapascal, and ultimate tensile strength is 130 gigapascal. Thermal conductivity is 5,300 watt per meter Kelvin. And electron mobility 20 centimeter square per volt second. Conductivity is 10 to the 8th Siemens per meter. And optical transparency is 97.7 for monolayer. And thickness is very thin, 0.355 nanometers because of one layer atoms. Comparators, the steel, modulus 200 gigapascal. Thermal conductivity 429 watts for silver and 400 watts copper. And electron mobility 1,400 for crystalline silicon. And electrical conductivity is only 63 times 10 to the 6. So if you just hear from the material scientists, they will say, okay, this graphene is so nice, right? The properties are so high compared to competitors, but we need to take this with a grain of salt, right? Because when we compare materials, for comparators, that's bulk property. For graphene, people are talking about single crystal graphene, right? So we're not so interested in other properties. For us, electrical conductivity, graphene, although it's not that high, but it's still electroconductive. And optical property, 97.7 transparent. So we're using these two properties of graphene material. In addition, it's very thin, so we can use these properties there are a lot of applications, right? We don't have to focus on single crystal graphene. We want to focus on large area graphene because if we can make this material electrically conductive, optical transparent, you can use it for a lot of applications. So speaking of applications, you can easily read from the web. This company is called Nanograph. So they listed 60 application areas of graphene. You have to trust every one of them, but this is a very interesting blog you can read. The application areas they point out, there are solar cells, batteries, heavy water production because of membrane, fuel cells, drug gene delivery, dialysis, biosensing, UV sensors, wearable electronics, flexible touchscreens, transistors, and so on and so forth. You don't have to trust every one of them, but if you read through the list, some of them do make a lot of sense, right? For example, you can use graphene in solar cells. Solar cells are very important for energy harvesting. If you can roll it up, there's a huge market for solar cells. So if you're interested in solar cells, there are electrodes, top electrodes, bottom electrodes. In the middle, there's active material. So when you have sunlight coming in, and then the photon energy strike out the electrons, so you can collect the charges. So you can collect the charges to generate electricity. On the top layer is very important. That layer has to be optical transparent to allow sunlight to pass through, and also it has to be conductive. So currently they're using ITO, indium tin oxide, but ITO is, the element of indium is getting less and less. The raw material is also very expensive. The process of making ITO, coating process is also very expensive. So if you can replace ITO with graphene, graphene is very easy to make. If you can make it right in large scale, there's a huge future for that. And if you can make graphene in large scale, replace ITO, you can make flexible solar cells. And you can imagine you can just place the flexible solar cell on a vehicle top. In the summer, you can collect a lot of electricity, and also a lot of applications like umbrella. You can put solar cells on umbrella to collect solar energy, convert it to electricity. So let's look at how we can make graphene is made nowadays. The graphene fabrication method basically can be classified into physical methods and chemical methods. In physical method, you use mechanical exfoliation or liquid phase exfoliation. Those methods, you can only produce a graphene platelet. So you start from graphite, and then there's some process you go through. You intercalate, graphite, you separate platelet into graphene platelet. The platelet is really very small in the micron range. It's not large scale. And then you use it. How do you use it? You just make a severely and coat it on some surface. So the property is not great, but it still satisfies some applications. There are chemical methods, reduction of graphene oxide, that's one, and epitaxial growth, that's usually you grow graphene on top of certain wafer, so you can make this basically for microelectronics applications. Very high quality graphene, but it's not very, it's not very large scale. Chemical vapor deposition, you have AP CVD and low pressure CVD and the plasma enhanced CVD. So those are the methods that has potential to grow large scale graphene. In our lab, we studied LPCVD methods. This is one student. He modified the standard tube furnace growth method. He put tube furnace on a platform so you can move back and forth the furnace relative position between the sample and the furnace, so that you can study the cooling effect, and that's turned out to be a major effect. So we can only grow samples in our lab. This is the quality of the graphene. So this from the students' work. Now you control the gas concentration from between methane and the hydrogen, and control growth time, growth pressure, growth temperature. That's cooling rate. Those are regular growth parameters. And you use Raman shift to detect Raman mapping to detect graphene. So usually you're looking at G peak and 2D peak. If the ratio is between above 2, then you know there's a monolayer graphene. So that's the purpose that's the goal we shoot for. We want to have monolayer graphene. And you can use Raman mapping to figure out if the growth high quality, large scale, large area. But no matter how you try it, there's still some defects in it. There are some wrinkles, which may not affect the property that much, and there are green boundaries. So it's like any growth process. You have grains, and then grain will start to nucleate. Graphene will nucleate, and then grow patches, and then the patches will start to connect to form a single sheet. So almost all the graphene research has been focusing on growing quality small-scale graphene, but there are research focusing on large-scale growth. So they use row-to-row process. They can grow. They put the furnace, and they have rows of substrate material for single layer graphene. Most suitable material is copper, and you just unwind the copper row going through the tube furnace, and then you wind it on for the finished product. Everything has to be in the controlled environment, so you send in your gases, the supply material stock, and you grow graphene, single strip of graphene. You can grow longer depending on the facility you have. And this is another study from MIT, John Clark's group. They were growing graphene strips. It's all in control, and they varied some of the conditions in the tube, so trying to study the effects of process parameters and graphene quality. So we worked with a company, Astrom. They supply a row of graphene, so they intend to supply rows of graphene, and we can study how to use this graphene. So our research, since people have been working on graphene growth, row-to-row growth, our research has been focusing on row-to-row transfer. So if you have a supplier to supply rows of graphene, we're going to put it on our machine to transfer it onto some substrate, usually transparent polymeric substrate. And that has turned out to be very challenging. Currently, graphene transfer has been using wet transfer, where you use chemicals to dissolve copper substrate. So you laminate your polymer onto the graphene on copper or other substrate, and then you go through chemical baths, you delaminate, you dissolve copper, and then you have this graphene will be transferred onto your polymer substrate. So Sony has developed this method. Well, the problem for that is because there's not much tension involved in the process, you basically have better quality. Okay, there's not much disturbance. However, the problem is, you have to sacrifice the gross copper, which is cost, right? Production cost, and the dissolution time is long, so you have to slowly dissolve the copper. And because you use chemicals to dissolve copper, they always introduce chemical contamination on the graphene. So when you make a graphene, you want this graphene to be pristine. There's no contaminations, no charge attached to the graphene material. So later on, when you use graphene material, you can dope it, you can do other process, you can make graphene useful. But for chemically dissolved copper, you do have pre-doped graphene, so change the graphene property already. Another method is called electrochemical delamination. In this process, you laminate your graphene with polymer, and then it goes through electrochemical baths. So you supply electricity to generate hydrogen bubble inside in this interface between your graphene, copper, and the top cover polymer. So this is the substrate you want to transfer the graphene to. Because of bubbles generation, you could have damage because microjets, the bubbles will disappear, introduce microjets that could damage your graphene quality. And also this process is very, very slow. If you do it too fast, then you have quality is damaged, even more. And also you use electrolyte that will contaminate your graphene also. So what we are doing, we're trying to develop a method that is dry. We also want to do large-scale graphene transfer, so it's a roll-to-roll process, but we don't want to introduce any chemicals. So in the process, we're trying to use graphene dry transfer process. So we laminate our top cover, transparent substrate, onto graphene on copper. We mount it on our machine, and then we can delaminate using peeling method. So this is a purely mechanical peeling method. It's not very easy to do, but especially, my colleague has been doing just a simple using just a simple coupon and then using tensor machine to delaminate the graphene from the substrate, gross substrate. Now we're putting it on roll-to-roll machine. The process is even harder to achieve. So the method, if you were using dry method, the cost is low. Transfer process is very fast because we're peeling it. And then there's no etching involved, so no chemical contamination. But, understandably, the quality might be sacrificed a little bit, and the process itself is complex. That's why we need to do very good control to control the process and then improve the quality. So initially, first step is to design this roll-to-roll machine. So when we design the machine, we're not thinking about graphene transfer alone. We're also thinking about transferring printed electronics. So another very popular field right now is you want to print flexible electronics. So you print your substrate, your device on one substrate, and then you grow some other device on some other substrate, and then you want to transfer your printed device onto you grow some other substrate and make it one integrated device. So we're thinking of printed electronic transfer also. So as you can see, the design concept is you have some certain of device you printed, and then certain areas you don't have that. So during the process, you could have sticking and slipping, different actions. About graphene, so we are about mechanical transfer. We are developing a model. So we develop a model to model this process. Although it's a roll-to-roll transfer process, can be a whole process, but what's important is only this peeling front over here. So we have two guiding rollers, and we have an unwinding roller, and there's two rewinding rollers. So this is the web is laminated polymer with graphene on copper, and after the peeling front, we're going to wind the peeled transferred graphene onto transparent substrate, and then the copper is going to be recycled for further process, and you can reuse it for graphene growth again. We develop a model to model the energy balance. So whenever you generate a crack in the peeling front, and we try to balance the energy release rate and the adhesive energy. Because you could have a process disturbance, or you're peeling some devices, and then you're not peeling some certain devices, so the adhesive energy could change. So the process could shift between peeling, not peeling, or peeling adhesion energy is high, adhesion energy is low. So the process map could switch. That presents a very high challenge to control systems. So we develop system model, and then we develop a peeling control framework, and then we can control our process. So a little bit modeling and simulation. So basically, we use energy balance. So we have this is an energy release rate and adhesive energy. And then we have energy balance and force balance equation. Then we develop a simulation model. This this will run. So basically, initially we start from controlling the tension. So we have three parts, right? We have incoming web, we have also web going transferred graphene, and also recycled copper. So there are three webs involved in it. Three tensions, T1, T2, T3. We can control the tension, and we can control the peeling angle, where the peeling angle is over here. So you can see this is incoming web, and then after separation, you have two webs going out. And there's always a peeling angle here. We use theta and alpha to represent these peeling angles. You can see if you change the tension over here, your peeling front is actually moving because of the balance between energy release rate and adhesive energy. So this peeling front, depending on the tension, it's actually very hard to model because this is peeling front geometry. You have to define the speed, you have to define the angle, and then to find where it is because it's in the planar 2D surface. So we developed this model, and the model works very well. And then since we know when we switch, when we change tensions, we can change the peeling angle. And reversely, if we develop a reverse model, right? So we can inverse the model. The model will give us, if in any case we want to control the peeling angle. So for peeling process, peeling angle, as you can see later on, is very important for quality too. If you want to have certain angle, can we set the tensions to control the peeling angle? So this is our control, process control idea. So we want to set the angle. This is a simulation result. If you want to achieve different peeling angles, can we calculate tensions we needed to give us that desired peeling angle? And the answer is yes, but there are some disturbances. The angle tracking is not that great, but you have to control your system to make sure they will satisfy the result. So in the end, we develop a supervisory controller. The supervisory controller is, for the model we have, is we're using tension, and we also have an input variable that's input speed. So we, based on these four parameters, we'll estimate peeling velocity of VP. That VP is the peeling front velocity, so where it goes. Sometimes VP will stop, because if you didn't control the process well, there's no peeling happening. So the peeling front is going to shift to different positions. There's no stable peeling. And that's not desirable in the peeling process, because we want to have a continuous peeling to give us controllable quality. If the peeling stops, then once it's resumed, it will generate some disturbance and generate defects in the peeling process. So we estimate peeling velocity. If the peeling velocity is greater than 0, then we can update our adhesive energy estimation using the energy release rate. If it's not, then we have an algorithm to estimate the adhesion energy. And then we'll solve for the tensions we need to give us a desirable angle to follow this reference angle. So this supervisory controller works very well, so we can have our tensions determined, and we can use this tension, send it to the lower end regulator, which are PID controllers. So the simulation result shows now if you have a desirable peeling angle, theta and alpha, and then we can control tensions. So by following this tension control, then we can have a desirable angle following. But you see there are still errors between desired angle and the actual angle. So what happens is, during the process, we estimate peeling speed, right? If you have an angle change, if say there's a desired angle in the process, if there is a desired angle change, the peeling front may not happen anymore, because during that period of time, the configuration of the T2, T3, and T1, it doesn't satisfy the peeling condition. So this peeling front has to move to another location during the move, you're trying to approach that criteria, which is your strain energy release is equal to the adhesive energy, then your peeling will happen again. So there's a period of time where peeling front is 0, and then after your peeling configuration is shifted, then you can start to peel the graphene again. So with those machine developed, there's actually there's continuing effort to continue design the control algorithm so that the machine the accuracy is much higher and reduce the offset and also reduce the overshoot. So that part is still going on. Another student worked on, just use this machine, we want to peel graphene. So this graphene material, well, although it shows copper web on it, but since we don't have rows of graphene, so our our solution is we mount our graphene samples, which is smaller size, is 10 millimeter by 30 millimeter. Still, in the regular size, is still huge compared to people do graphene research. They only look at 13 micrometer size graphene. So this is still huge size graphene samples. We attach the graphene samples onto our carrier film, and then we can start to study the peeling characteristics of graphene. So we did a process study. We studied the speed and tension effect, and then we also looked for characteristics of the graphene, and then we did large scale 3 inch by 3 inch graphene peel, and we also studied the adhesion energy effect and also controlled angle effects for graphene transfer. And then after that, we are looking for applications for graphene. So first of all, for graphene quality, especially on this large sheet, or comparatively large sheet, 10 millimeter by 30 millimeter, we want to measure the surface conductivity and also the uniformity of transfer quality. It turns out measuring conductivity of graphene on surface is not that easy because the resistance is relatively high. So we made an array of gold electrodes on the surface, and those gold pads are 1.5 millimeter by 1.5 millimeter square, and the distance, the gap between the among the electrodes is also 1.5 millimeter. And we use 4-probe method to measure the conductivity. But the conductivity we measure in the center and in close to the edge, they're different because of the electric field distribution. So we did a console simulation. We figured out correcting factor so that we can measure it. We can correct the edge effect of the measurement. So once with that, we took average resistance measurement. We under different peeling tensions, 5, 10, 15, and we ran the machine at different peeling speed. So you see, obviously, the quality of the samples are dependent on the peeling tension and also peeling speed. The lowest resistance or the highest quality we have been able to get was when we use 10 Newton peeling. Of course, this is just a process parameter based on the sample size. So around 10 Newton and 2 meter per minute peeling speed. And of course, the student will draw. We're not only looking at average resistance, we'll also look at the standard deviation, and then you can plot a Pareto chart, figure out which direction, which conditions are the best. The conditions over here, we want to have average resistance as low as possible. That indicates higher graphene quality, and also the variations as low as possible. So in the end, we decided to use 2 meter per minute and 10 Newton as our best quality, best parameter to give us quality. And then we transferred a lot of samples, and we want to further characterize the properties of the samples. And one property that electrical engineers, when they make microelectronics, they're interested in is electron mobility, and also, when you make a fat graphene-based field effect transistor, you're worried about gate source voltage, that's direct voltage, so V direct, and also the leak current between your gate and source. So what we did is we made a simple graphene-based field effect transistor. So we have a gate electrode, and on the gate electrode there are hydrogel material. So this is a substrate, and we put our transferred material, transferred graphene over here. So this is a very large channel for if you were working on graphene-based field effect transistors. So we have a channel size 3 millimeter by 5 millimeter, and we have gold electrodes, source, and drain. So we use this field effect transistor to study the properties. We scan through the voltage. So when gate and source voltage scan from negative 4.4 volts to 0.5 volts, and we measure the drain source current. So the behavior of this is you have initially you have a large current, and then when the gate source voltage becomes 0, you're supposed to see there's no current flowing through drain and current. So your gate and source voltage is controlling the current flow between drain and source. And you can use this shift to detect if you have a substrate or some species on your hydrogel. You can detect the species, and you can use this as a sensor. So first of all, the charge neutrality point. If you have a V direct, so this voltage you call V direct, for a lot of wet etched, because we did a lot of comparison between dry transferred graphene and wet transferred graphene. So for wet transferred graphene, V direct, this voltage is almost all shifted to 350 millivolts. So further away from the zero volt. That's because of doping effect, because you have wet transferred chemical ions, so their ions get doped on the material. So you see a doping effect there. For rotor transferred graphene, our V direct is almost close to 0. So this shows our graphene is pure and is not affected by doping. To summarize the results we have over here. So this is wet transferred PET, graphene on PET, wet transferred, and this sample is wet transferred graphene on polyimide. Both of them have high V direct, so this shows charge neutrality is not good, and our samples are close to 0, so it's very good charge neutrality. This is very important for following on processes when people want to use a graphene to build sensors and field effect transistors. For transductance, our dry transferred material is still low compared to wet transferred materials, but they're on the same order. So it's not that lower than the wet transferred graphene. Another characteristic we're looking at is the leak current between gate and source versus drain and source. You want this leak current to be as small as possible, because if you have large gate current, that's not field effect transistor anymore. So for wet transferred PET and wet transferred PI, so those are graphene on PET and PI. Those samples, they have very high leak current, so that's not good for field effect transistor. Whereas our dry transferred samples, they have very low leak current. That means the quality is better for electronics applications. So the largest samples we have been able to demonstrate is 3 inch by 3 inch. It's already huge comparing to other transfer samples. It's also in roll-to-roll process. So we take this 3 inch by 3 inch samples and we mounted on our rotary roll machine. We peeled it, and this is a transferred 3 inch by 3 inch graphene on PTEVA. So, and then we use field effect transistor to measure mobility of the sample. So this is the map. We took them, we sectioned them into smaller pieces, 6 by 6 pieces of samples, and then we use those pieces to build GFET, and then we use GFET to measure mobility. So this way we can measure mobility at each location, and then we can map the quality of the sample. So in the end, we got very uniform quality of the sample, except there's 2 corners. Those 2 corners are actually, we use tweezers to pick out the samples. So those 2 corners has the samples were damaged a little. So this 2 corners doesn't have very good mobility measurement. So electron mobility is important characteristic for electrical engineering for electronics. We compared our mobility value with wet transferred mobility values. You see the rotary roll, this work is right in the middle of wet transferred. So comparing the mobility itself, charge mobility itself, wet transferred samples and dry transfer samples, rotary roll samples, they're comparable, very much comparable. And our sample has better quality because they, within the center, the version is smaller. But if you look at the dry transfer samples, where people use small samples to do dry transfer peeling experiment, you can get higher mobility values for dry transfer. This is from one of the studies, a little higher mobility values, just using graphene samples, right, small size samples. And another study reported, similar millimeter scale GFETs, similar results as our rotary roll samples. If you're measuring, if you use a small, micro scale samples, which means the channel size I showed you, our channel size is 3 millimeter by 5 millimeter. If you make a channel size very, very small, like in a micrometer scale, you can get higher mobility. But it doesn't mean too much because you're looking at only one spot, right? Whereas we're looking at whole surface. So this is a video showing the actual transfer process. So the reason I show this is to try to introduce a peeling angle effect. So the first sample we peeled is 2 millimeter sample, and you see 2 centimeter sample. And you see it's effortless, right? The peeling front doesn't move a lot, and you have the width of the sample is 2 centimeters. So it's peeled very easily. This is 2 centimeter sample. And this is 6 centimeter sample. Because the width of the sample, peeling front, the width of the sample is changed, so your peeling effort is going to change, right? So the 6 millimeter sample will need to have the peeling front move to a certain location so that you satisfy the peeling condition, then the peeling can start. So the reason for that is during the experiment, we noticed the peeling angle will change. So we decided to study the peeling angle effect. But at that time, our machine still cannot do, the force range is not wide enough, so we cannot use large force. So what we did was we choose a lower force, 5 Newton, and then we vary the width of the sample, starting from 2 centimeter to 10 centimeter. And then this will give you different peeling effort, right? Different peeling angle. So we measure the peeling angle for 2 centimeter with sample. The peeling angle is 34 degrees. 4 centimeter is 41 degrees. And then for 6 millimeter sample, we have 65 degrees, and so on and so forth, all the way to 10 centimeters. Of course, the peeling energy is required is higher, much higher. Then the peeling angle is 105 degrees. So we use both 5 Newton on top and bottom. And then we use SEM to look at the samples we obtained. For peeling angle at 34 degrees, we see a lot of of these dots over here. The white dots indicate there are certain areas of graphene is not transferred because under SEM, graphene is conductive, right? Under SEM, you're not supposed to see white dots as charge concentration as those white dots. So at white dots, that means there are certain areas of graphene we didn't peel, so it didn't transfer. And then as the peeling angle increases, we see better quality. 6 and 8, we see better quality. There are some small, over here, those are graphene boundaries. And those are small compared to those big white dots. And when you have a 10 centimeter width, now you have both defects and also cracks formed in the graphene because maybe the tension force compared to that is quite high. So that's not good for graphene quality either. So we look at the Raman shift of all the samples. They all have, this is a Raman after transfer, Raman shift on of graphene on PVA. So we transfer this material, graphene onto PVA. This is another type of material we transfer onto. It turns out it's not very easy to get Raman shift, Raman peaks for graphene on PVA because PVA its own has Raman peaks, and so all those peaks are contaminated by this. So we did a round Raman shift, and then we compared this and this. So we were looking at 2D peak and E peak, and by this we can still GP. So we can still determine the graphene transfer and also the number of layer of graphene. So 2D over G intensity ratio is all about 1.5. So that's the confirmation of the transfer graphene monolayer. And 2D positions and G positions, 2P positions, they're typical graphene positions. And then we looked at the peeling angle effect graphene coverage. So we took SEM, we can use SEM to calculate what is the graphene coverage ratio. So you can see when the peeling angle is small, we only have 90, well, it's already pretty high, around above 90, around 95 coverage. But if you have a peeling angle at 65, 77 degrees, graphene coverage is really, really good. It's almost 100%. We also did mobility measurement and see the mobility. When you have larger area, graphene mobility is obviously also higher. So we started to look at a little bit what's the effect of peeling angle, right? We did some mechanical analysis. Of course, the peeling force can be decomposed into perpendicular and shear. So you can study that, but in the end, it's all adhesive energy related. So we did. I'm going to switch here to adhesive energy study. How much time do I have? 10 minutes left. So maybe I can go 5 minutes. 5 minutes. I can just go through this quickly. So for graphene adhesive energy, it's actually pretty important characteristic because there are a lot of people, they measure the graphene adhesive energy and the reported value are not consistent. So a standard method is blister method. So this is some other people's work. They measure the graphene adhesion energy on silicon wafer because silicon wafer is important, the substrate. If you want to build microelectronics, they want to transfer graphene onto silicon wafer. So they measure the adhesive energy between graphene and silicon wafer. So keep in mind this is transferred graphene. So you have to grow graphene and then transfer, lay it down to silicon wafer, and then measure the adhesive energy between silicon wafer and graphene. So the reported value is 0.45. For multilayer is 0.31 joule per meter square. And another study measured the adhesive energy between transfer graphene and copper. It's one step closer because they're measuring adhesive energy between graphene and copper. So the reported value is 0.51. And this is the typical blister test. So what we did is, what we need to know in terms of control the process and understand the peeling behavior is, we need to understand the adhesive energy between graphene and copper in the as-grown setup, right? After you grow graphene on copper, what is the adhesive energy between as-grown graphene and copper? So we use the same blister test setup. Basically, you have interferometer microscope looking at the top of the sample. So we made a PETVA graphene on copper sample. It turns out this sample is very hard to make because it's not transferred. We have to drill a hole through underneath and then supply pressure on it so you can see the blister forming. You measure the height of the blister to back calculate what is adhesive energy. So, coming from a traditional manufacturing background, we know how to do manufacturing. So this is actually nano positioning stage. We use nano positioning stage and an end mill to drill a small hole and then measure the conductivity between the tool and the sample. Whenever we see connected, you know you reached copper. And then this is backing plate, polymer backing plate. You have to have this to make sure the sample is not deformed due to the big pressure over here. And then after drill a hole, then we use electro polishing method to remove the copper. We generate the hole to reach the graphene surface. So yeah, this is the actual test we did. Just on top, you have PTVA graphene, and you have a hole through copper foil, and then we supply water, and we use water to increase the pressure. You see the fringes, interference fringes form, and you can count how many fringes there. You can calculate the height of that. And then at the last moment, it's going to delaminate. So the fringes will disappear, and at that moment, you calculate the final height, and you use that. Yeah, that's when it's disappeared and failed. So that's delamination, and you use that to calculate. So this is a central deflection, and this is the pressure you introduce, and use the pressure and the maximum height. You can find out adhesive energy. So our measurements between 0.74 to 1.53, depending on the surface roughness of the sample. So we also characterize the surface roughness of the copper, and then determine what is the adhesive energy, as-grown graphene adhesive energy. So this is the first time that people have reported as-grown graphene adhesive energy using standard method. So we also did adhesive energy estimation during the rotary process. We can do similar modeling, and then during the process, we measure tension. We can estimate the adhesion energy also, just based on the tension measurement during the rotary process. And that's important because, in the beginning I told you we're not only interested in peeling graphene, we're also interested in peeling printed electronics. So inline in situ estimation of transfer of adhesion energy is important for control. So we were able to estimate the adhesion energy by correcting bending energy. There's a lot of process going on in the peeling process. So the result we get is actually similar to the result we get from blister test. So that's another way of estimating adhesion energy. So in the interest of time, I'm going to wrap up my talk to give you some summary points and conclusions. So first of all, as you have seen, I hope you have realized that large-scale graphene has potential for a lot of applications. If we really can break the barriers and push this field forward, you will find a lot of applications. But growing and transferring large-scale graphene is still challenging. In terms of the crystal size and reduce defects in the transfer process. So there are efforts in Korea and in other particle world, they're growing single crystal graphene. So if you can, grow single crystal graphene, all the problems in the transfer process will be gone because single crystal graphene is strong, right? No matter how you peel it, it's going to be peeled. It's not going to crack. And there's no defects in it. So my former colleague, Rani Ruoff, in their group is trying to grow single crystal graphene, but I think the largest crystal size is still under a millimeter. You still have those defects in graphene. In the process we developed, it can be used to transfer large-scale graphene, although the quality, the resistance is still, surface resistance, right now we quantified surface resistance, is still in the kilo-ohm range, but it's compared on the same order as wet transfer graphene. And dry transfer graphene has a lot of advantages, including there's no chemical contamination, process is fast, you can recycle the graphene growth substrate, so that's a big benefit also. And then the transfer process, can be used for a lot of applications. So just a few more points on our ongoing and the future work. So the dream is obviously, produce large area, high quality graphene in a low cost fashion so that we can use it to make applications. One of the immediate application is solar cell. So you can replace ITO and then make organic solar cell flexible, make a flexible solar cell, then we can use it in a lot of different applications. Particularly, there is a potential you can build a transparent solar cell. So you can have certain light components transmitted, so you can still see through, but you can also, in the meantime, collect electricity. So one of the other benefits of graphene is if you compare graphene and ITO, graphene has a wider, the light spectrum. So you can collect more sunlight to convert it to electricity. ITO, on the other hand, is probably good for visible range, but not so good at other bandwidths. And then the second application area is wearable electronics using graphene-based biosensors. So one of the figure I showed that's basic idea of graphene-based field effect transistor. We can have electrodes and the substrate is graphene, and you can put chemicals on it and put a gate electrode in the solution, and you can measure the chemical concentration or chemical species in the solution. So that's another area that we're working on. And then, of course, we're continuing developing this rotary process. We're trying to be able to control the number of layers during the transfer process. So if you can grow multiple layers in growth process, we can control how many layers we can transfer. That's another area of the research. All right, so the work I have been presented, this partner work is supported by NSF, a Nathan Center project, and also a roll-to-roll manufacturing grant. The work, all the work I presented are done by graduate students, former graduate students, Xin Hao and Wei Li, Kishan Zhao, and Nan Hong. All graduated already, and then collaborators Ken Lichty, Dong Mei Chen, Deziak Wende, and Dmitry Kiriv. Dmitry was a postdoc working with Dr. Wende, Desi. He's now a faculty member at Maryland. So with that, thank you for your attention and participation. Happy to answer any questions.
Due to the time, we'll get only one question.
Yeah. So, for me, when I was doing tests, like normal tests, it's really difficult to find the first thing. So I know, like maybe, like for that, what you are doing is for the adhesion, the energy. So how does that work? Because I feel like it's the adhesion energy on the PDA, for example, is more like adhesion part doesn't make so much sense for me.
So it depends. So if the adhesion is there, right? But initially, when you peel, in the starting point is actually very important. That's why the peeling angle plays a big factor there. So when you change the peeling angle, the peeling force actually can be decomposed into two components, and then there's a mode mixing. In adhesive mechanics, there's a mode mixing how you can separate to bonded bodies. So people have been looking at mode 1, mode 2, the combination of those two. Where is the sweet spot that you can separate those two? Even for simple like dry peeling samples, when they make a sample, they want to peel it using pencil machine. It's not 100%. So for us, we can control tension, we can change the peeling angle. I didn't show you the results. Actually, even for a 30 millimeter sample, the beginning of the sample, the quality is always worse than the end. So there is an effect. But if you're talking about roll-to-roll peeling, right, we can discard the first few centimeters of material. Yeah, and then we can just focus on the rest. Yeah. That's a good question.
So I have one question. So you said when it starts to delaminate, the quality is not good. So but in the point of the friction mechanics, can you intentionally kind of induce the initial crack to enhance the delamination quality?
Yes. So that's what they do in the sample peeling dry peel samples. Sometimes they do introduce an initial crack in the sample peel. Yeah, and there are people, my colleague, perhaps to model this using IBM to model this process. It's not very easy to model either.
Right. So we have more questions. Then let's thank him again for sharing.
So when I did a postdoc, I did a graphene transistor shortly, and yeah, and then at that time I did the Scotch tape, and then
That's a Euro way.
yeah. So.